Okay, class, I'm just making this video because there was an issue that came up on the bonus that I had given with the Bessel functions. I think it was number 36. Anyways, I want to run through something when it comes to the derivative of a power series. We were given in class that if you try and take the derivative of the power series, so you have your c sub n, then you have x to the n, that the formula for this was that you basically left the c sub n alone and then applied the power rule to the x to the n power, so that this became summation n equals, I'll leave that for a second, infinity to infinity. The c sub n is left alone, and then power rule on x to the n is n x to the n minus 1. And we would shift our index from 0 to 1. Now, let me explain to you a little bit more why this works. First of all, on the left side here, this is just, if we plug in 0, we get c sub 0. Then we plug in 1, we get c sub 1 x to the first, plus then c sub 2 x squared, plus c sub 3 x cubed, plus forever. Now, if we differentiate this now, so take derivative of each of these terms, the derivative of the constant here is 0. So that's an important step right there, that this becomes 0. Then we have plus c1, plus now the c2 is a constant, so 2 comes out, 2c2x. Here the 3 comes out, so 3c3x squared plus forever. Now, we can see from this that this sum, we can rewrite this as in this sigma notation, n starting at 1, and that's because we don't have this term. So, or it's a 0, so we want our index to start here at 1. It'll be c sub n, and then the power on x will be, sorry, I forgot something here. The n came out, sorry, there's your n in front. So n c sub n x to the n minus 1. So for every one of these terms that we have the n in front. The power on x is 1 less than n, so here it would be 0. Then we have our c sub 1. Here's our n. The power here is 1. That's n minus 1. And then our c sub 2 is in front. And that pattern continues the whole way. So this matches our formula, and therefore this formula is correct. So I just want to clarify that first. That's what we knew already, but hang tight here. There's something I want to show you. It's tricky. Let's try something like this. If we did take the derivative of the power series, and I'm just going to let my c sub n be 1, x to the, let's say, 4n. Okay, so this is a specific example here, n equals 0 to infinity. Then the derivative of this should be sum, I shift my index 1, n is 1 to infinity of, now what we have here is our x raised to the 4n, so the 4n will come out in front, and then we reduce that power by 1, so we subtract 1 from the power. That's what it should be. Let's see if that's what works, or let's see if that's what it is. So what I'm going to do is I'm going to write out what this was. So I want the derivative of, let's see, if we let n be 0, we're going to get x to the 0, it's 1, so we get 1 plus, now if we let n be 1, we get x to the 4th, plus if we let n be 2, x to the 8th, plus let x be 3, n be 3, x to the 12th, plus keep going. Now this is equal to, take derivative of each one, 0. Again, the derivative of 1 is 0, plus 4x cubed, plus 8x to the 7th, plus 12x to the 11th. Now let's check that what we get here is this summation right here. Let's just verify that those are the same. So let's just try this. Let's let n be 1 here. If n is 1, we get 4 times 1 x to the, let's see, 1 up on top, 4 times 1 minus, that's going to be 4 minus 1 is 3, so we get 4x cubed. That's that term. Plus, now let's let n be 2. We get 4 times 2. X to the, let's see, 4 times 2 is 8, minus 1 is 7. So that gives us 8x to the 7th. That's this one. And then the last one would be 4 times 3. X to the, let's see, 12 minus 1 is 11. So that's 12x to the 11th. That's this one. So it appears that that works. And this is all good. So again, we're okay with this. Let me show you where we run into some issues and where you have to be very careful. So I'm going to start a new page. If we have something like this, n equals 0 to infinity, and we want to take the derivative here of this summation, and let's say, again, we have 1 here for c sub n, but then we have x to the n plus 1. Let's see what happens here. If we go with our formula, we should have sum n equals shifting the index, right? We shift it to 1, and then we bring out the n plus 1 in front, and then we have x to the n, so we subtracted 1. Let's see, is this correct? It's going to turn out that it's not, and let's see what's going on here. First of all, let's write out some of these terms. If n is 0, we get x to the 0 plus 1, that's x. So we have derivative of x, and then now if we let n be 1, we get x squared, and then n be 2, we get x cubed, and then n be 3, we get x to the 4th plus dot dot dot. Now go ahead and differentiate this, and we get 1 plus 2x plus 3x squared plus 4x cubed plus dot dot dot. What you'll notice here is something critical that has not happened before. The derivative of that first term was not 0, and that's because when we plugged in 0 into our series here, into this formula, when we plugged 0 in right there, we did not get a constant. We actually got x to a power, and therefore its derivative will not be 0. And let's just see now, I'm going to take that parenthesis off. Let's just see that this formula is not going to create this list. So what we have is, let's see, n is 1. If we let n be 1, we get 1 plus 1, that's 2, x to the 1, plus, now let's let n be 2, we get 3, x to the 2nd power, then we'll get, n is 3, we get 4x cubed, and then we keep going. Now, certain things do match up. We have 2x to the 1st power, we have our 3x squared, we have our 4x cubed, and everything else should be good. So we're good out here with the rest of this. But what we're missing here is that 1. So the reason why, again, is because when n was 0, we did not get a constant here. So we're going to have to change something here. Something has to adjust. And really it just comes down to this index. We started at 1. The only reason we ever shift our index like this is if the first term of this series is a constant. So if you're looking at a series and you're going to differentiate it and you know the first term is a constant, then you shift the index. If the first term of that is not a constant and it has a power of x in it, then what you're going to need to do is leave your index alone and not switch it to 1. So we'll leave it at 0. And let's just look at this here. If I were to have not switched that index, left it here, but then kept the formula that we had, x to the n. So that was your derivative. Then, hold on, my phone's ringing here. Then now let's write some of the terms here. So let's let n be 0. If n is 0, we get 1x to the 0. Then we say plus. Now let n be 1. We're going to get 2x to the 1st, then 3x squared, then 4x cubed, dot, dot, dot. Now we have everything. We have our 2x, 3x squared, 4x cubed, and the all-important here, that's really just a 1, right? X to the 0 is 1. So that gives us our 1. So the moral of the story is be very careful when you're looking at a series and you're going to differentiate it. Whatever's in here, your C sub n x to the something. Now, depends on what it is here. Whatever that is up there, if you plug in n equals 0 into this, and you do not get 0, you get some power of x, then you know that the derivative of that first term will not be 0, and therefore you can't shift the index. Now, it doesn't come up very often. In fact, there aren't many examples that I did in class, or any examples that I did in class where we would have run into this problem. But on the bonus question for the Bessel, you would have run into this problem and would have had a really hard time with it unless you recognized that you do not shift the index on that derivative. So, okay, I hope that clarifies something. I just didn't want to leave that unresolved. If you have any questions, let me know.